In this video, I'm going to talk about functions that increase and decrease, and I'm going to very quickly talk about something called function notation, which is when we plug a number into an equation. When we look at a graph, we're going to read the graph from left to right. So if you find the leftmost point of this purple graph, which is down here, I'm going to start there, and then I'll put my pencil on it and follow the curve. Well, as I follow the curve, what's my pencil doing? Going up or down? Well, it's going up, right? When the graph is going up, that means the y values are going up, and we call that increasing. Well, then when I hit that black dot at the top, the graph actually changes direction. Now my pencil's going down. It's going down until I hit this black dot. So we say the graph is decreasing. And then the graph changes directions, and my pencil goes up again. So we say the graph is increasing. In other words, when you read a graph from left to right, if you put your pencil on it and your pencil's going up, it's increasing. If your pencil's going down, it's decreasing. That means the y values are changing of each of the ordered pairs. Now, for what intervals is this happening? Well, remember, even though I don't see an arrow, the graph was here forever. Well, forever is infinity. Well, this is the negative side of the graph, and we're going to say that this graph starts at x is negative infinity, and it's increasing until we get to this x value. Remember, in an ordered pair, the first number is x. So this is the interval for which the graph is increasing. But then at that x value, it takes a turn, and it decreases until I get to this x value. And then at 2, it starts increasing again. And how long does it increase? It increases forever. Now I know you understand infinity means forever. So on the right-hand side of this graph, you're probably fine with infinity. On the left-hand side, you may not be so fine with negative infinity. Negative infinity is telling us that the negative x-axis goes to the left forever. The left was our negative x-axis on a number. Sometimes graphs don't have very much change in the graph, increasing and decreasing. So in this parabola, if I find the left side of the black graph, which starts up here, the first thing my pencil does is it goes down. That means it's decreasing. Now, we always call the left-hand side of the graph negative infinity because it starts at x equals negative infinity. And it decreases until this x value. That's when it changes direction and it starts going up, in which case the graph is increasing. It starts increasing at 1 and it does it forever. Now, we have some special cases. I want you to think about a linear function. Remember, linear is a graph that has a straight line. Well, if I put my pencil on this graph and follow it from left to right, I want you to notice the graph is going down forever. The graph doesn't have a change in increasing and decreasing. It just has one interval. And its one interval is that it decreases forever. So you actually can't put an x value on it because it's just doing it forever. Function notation. A lot of times we write equations of functions using this instead of y equals. You're used to equations that say y equals 2x plus 3. This is pronounced f of x. It's another way of writing y. The nice thing about it is that the number that appears in the parentheses is telling you the number to plug in for x. So here's what you got in Algebra 1. You would get a problem like, if y equals 2x plus 3, find y when x equals negative 3. And you would know that you're going to plug negative 3 in for x and evaluate that expression. This is the same problem. It says if f of x equals 2x plus 3, find f of negative 3. it's telling you that this is x, and you should plug it in for x in that equation. Now remember, when you do these problems, you have to do order of operations. So you have to do multiplication before you add. Although the nice thing is, if you're doing this on a graphing calculator, you actually can just plug it in and the calculator will spit out the answer. You've done function notation before, even though that's not what you may have called it. And it doesn't matter what type of function you're dealing with. So in this one, we're going to do a quadratic function. In the last one, we did a linear function. So if f of x is equal to x squared plus 2x minus 11, find f of 0. That says plug 0 in everywhere you see an x. It replaces every x because you got to get rid of the x. Well, 0 squared is 0, 2 times 0 is 0, and 0 plus 0 is 0, and 0 minus 11 is negative 11. Now, the reason I show you this example that you would never do in the real world is because you might get something like this. Let's say you work at a paper company and you're making reams of paper. Reams of paper are usually a package of 500 sheets of paper. And the way this works is that your operating cost is $800. That's not realistic, by the way, but I'm just to display how this works. Your operating cost is $800. When you run a business, you have these things called expenses. You have to pay for the building you work in. You have to pay for your materials. You have to pay for your workers. There's a lot of stuff that goes into it. And then you're making a profit of $1,000. Again, not really a reasonable problem. I probably should have come up with something better. So the equation that represents the situation would be 1,000x minus 800. So basically you're taking how much profit you're making and you're subtracting from it the cost of running your business. We want to find C of 20. How much money do I want to make if I make 20 reams? You would plug 20 in for x. And 1,000 times 20 minus 800. 1,000 times 20 is 20,000. And 20,000 minus 800 is 19,200. So again, I realize it is not the most reasonable of problems, but in the real world, when we're trying to figure out how much money we're going to make after we subtract our operating costs, it turns out it's really just a function notation problem. And that was increasing and decreasing on graphs and function notation.